So for the code walkthrough for this dataset, which is entitled Pipe Thickness Loss Prediction using a neural network. So for the first part, which is initial setup and imports, the coding starts from this line, #import necessary libraries, until this line. So for this part, we import essential libraries like pandas for handling our data, TensorFlow and Keras to build the AI model, and also sklearn for data preparation and performance evaluation. We also set a random seed to ensure that our results are reproducible every time we run the code. So that's for the initial setup. Next, we move to the second part, which is configuration and GPU check. So the code starts from this line, #configuration, until this line. So for this part, this section sets key parameters for our project, such as the path to our dataset and the settings for the model training, like the learning rate and the number of epochs. We also check if a GPU is available, which can significantly speed up the training process. So that's for the configuration and GPU check. We move to the data loading and pre-processing part, which is the coding starts from this line until this line, return XY. So for this data loading and pre-processing, there are three functions to perform this. There are three steps to perform this function. So first, it loads the data from the CSV file. Next, it cleans the data by removing any rows with missing values. And third steps, it separates the data into our input features, which denoted as X, like pressure and temperature, and our target output, which denoted as Y, which is the thickness loss that we want to predict. So that's for data loading and pre-processing. Moving on to the next part, which is model development. So the code take line from here to this line, return model. So for this model development, we build a sequential model, which is a stack of layers. It has three hidden dense layers that learn complex patterns from the data. We use dropout layers as a regularization technique to prevent the model from memorizing the data, which helps it perform better on new and unseen information. So the final layer is a single neuron that outputs the model's prediction for thickness loss. So that's for model development. And last part is main execution block. So for the main execution block, the coding starts from this line until the end of this whole coding line. So for this part, main execution block, the main function executes our entire project pipeline. First, it calls our function to load and pre-process the data. Next, it splits the data into training and testing sets and use standard scaler to normalize the features. This scaling step is crucial for helping the model to learn effectively. Then it builds the neural network and compiles it, setting the optimizer and the loss function. And the model.fit bracket command starts the training process using callbacks like yearly stopping to make the training more efficient. The model.feed command is like this, like on this line. Finally, after the training is complete, it evaluates the model's performance on the unseen test data and plot the results so we can see how well it performed.
Okay, next. This AI model, which has an R-square value of over 90%, has important positive implications for society and the environment and align with several UN Sustainable Development Goals. Key impacts: societal impact, safety. Model enables the shift to predictive maintenance, which can prevent catastrophic like leaks or explosion in industrial plant. By accurately predicting pipe degradation, this helps protect the life and health of workers and nearby communities. Environment impacts prevention. The model serves as an early warning system to prevent environmental disasters, such as chemical spill that contaminate water and soil. Allow engineers to intervene before a failure occurs, protecting ecosystem and preventing pollution. SDG 9. Industry Innovation and Infrastructure. The project builds resilience infrastructure by using AI to improve maintenance strategies. SDG 11. Sustainability, cities and community. By preventing industrial accidents, solutions help make human settlements safer and more resilient. SDG 12. Responsible consumption and production. The use of predictive maintenance promotes resource efficiency by allowing for targeted repairs and replacements instead of replacing entire section of a pipeline based on a fixed schedule. This conserves materials and reduce waste.
Real-world deployment strategy is to deploy this model in a real industrial environment, and engineer will follow this step. First, connect to live data. A data pipeline would be created to automatically feed real-time operational data from the plant's control system to the model. Second, integrate with a system. A trained model would be wrapped in a REST API, allowing it to receive new data, make prediction, and return result. This makes it a modular service that can be easily integrated into other software. Third, validate in shadow mode. The model would be run in the background to make prediction without taking any action. Its prediction would be compared to actual inspection data over time to confirm its accuracy in a live environment. 4. Create a dashboard and alert system. A user-friendly dashboard would be developed to visualize the predicted thickness loss and highlight high-risk area. An automated alerting system would be notify personnel when a predicted thickness loss exceeds a critical threshold. Lastly, monitor and retrain. A machine learning operation workflow would be established to continuously monitor the model performance for model drift. The model would be periodically retrain a new inspection data to ensure it remains accurate.